In the past months, we've been very busy getting our second-hand Tesla motor up and running, to make us a bit less dependent on current diesel prices. And with all the wiring finished, it's almost time to fire her up and see if she's able to move the boat. My name is Gijs, and this is my dad. And this is Schooner Tijgerhaai. 3 years ago, we started a major rebuild to get her ready for new adventures. And we're sharing the process with you. Subscribe to stay tuned. In the previous 2 videos we installed the electric motor and the lithium battery pack. But before we can actually switch on the batteries, there is some safety stuff that has to be finished. First thing is the emergency flooding system of the battery box. We installed and connected the fire pump in the last video, but we didn't run the pump yet or de-aerate the lines. So that's the first thing we have to do. I disconnected the water hose and I fired it up. And after a couple of tries, eventually the pump house filled with water, and now it will pump from the fresh water tank towards the battery box in case of emergency. So the hose can be hooked up again. Some may remember from the last video, for the total flooding system there's a temperature sensor on the lid of the battery box, which will switch on the pump at 100 degrees Celsius. And inside the box there's a sprinkler head which pops at 145 degrees. To make sure that the pump doesn't have to run for a long period against a closed sprinkler head, there's a pressure switch in the line just after the pump. It is a reused one from our old freshwater Hydro 4 unit. So it's best to check if it works as well. Here's a problem. The aluminum connection flange from the switch is cracked at the threaded part. I probably over tightened the half-inch connection a bit. High quality ones, like this one, are pretty expensive and they don't make spare flanges for this one anymore. So we made a new flange from leftover stainless steel parts. The old rubber membrane is not leaking yet, but it's showing signs of old age. So it's best to replace that straight away. To test it, we can bypass the temperature switch of the fire pump on the local cabinet. I do have to remember to make labels for this, sometime soon. The pressure can be set to a point where the pump stops when it presses against a closed line, and it starts again if the internal sprinkler head breaks. That was the last piece of safety equipment. So now we're technically safe to start using the batteries. But first I want to make sure the settings on our new hybrid inverter are correct, so that it does not overcharge or overdrain the batteries. The solar panels used to power our 24 volt hybrid inverter, charging the 24 volt batteries. But now the new high voltage battery will take over all the household equipment on board through the new inverter. So we'd rather have the solar panels charge the big battery and give the 24 volt one a small top up every now and then. With both inverters switched off, we can simply unplug the panels from the old one and plug them into the new one. Our current solar array is really at the top limit of what the Victron 24 volt solar inverter can handle. But for the new high voltage inverter, it's near its minimum. So there's a perfect band of overlap between the two. If there's ever something with the big inverter or the high voltage battery bank, we can always switch back to the small inverter and still be able to use the solar panels. The main high voltage battery switch is not on yet, but with only the solar power connected to the hybrid inverter, it can already be switched on, so I can check and change the charging and inverter settings to be aligned with the battery pack. With those correct, I know it will safely charge the battery, by solar, shore power or generator, and it can supply all our single phase and 3-phase power consumers on the boat from the battery. Now I feel comfortable switching on the supply of the battery management system, which will establish communication with the cells, and if all is right, it will switch on the contactors, making the high voltage DC system live for the first time. It took some tinkering, but we eventually got working communication between my laptop, the BMS and the battery. And I can read out everything about each individual cell. And also here I can check and change the safety values for temperatures and the charger and all that stuff. It all looks good. So if I close the door of the cabinet, the safety interlock loop closes, so the BMS gets green light to power the high voltage DC bus. That means the hybrid inverter is also connected to the system. So we can see if it does what it should. And we can check if the generator charging works as well. The Tesla motor doesn't get any power yet. It is still lacking its brain. We are not using the original Tesla vehicle control unit. For retrofits, it's common to use an aftermarket VCU because it gives way more customization options, which is especially important for us since we're using a car motor in a boat. This Tesla motor in a boat stuff is not done much, so no one has designed a specific ship's VCU for it yet, but with a bit of fiddling around, we can make it work with a car VCU. The one EV Europe recommended us is made by AEM Electronics, an American company which makes ECUs and VCUs for racing and performance upgrades to cars. That means there's tons of customizable settings. And by combining all those settings, we can make it do things that it would normally never do when installed in a car. The downside of so many possibilities is that it takes a lot of time to figure out how to make it do the things we want it to. Because this use case is not described in any manual, of course. I'm not gonna explain all the tricks we pulled to make it work. Unless you're interested, then hit me up. And we have to thank EV Europe here. They were very helpful in figuring out what would work best in our situation. I did install a couple of electrical boxes around the VCU for connections and relays for ignition and cooling pumps. Because this is a car VCU, it expects a reverse, neutral and drive signal, which is of course not how you maneuver a boat. We control forward and reverse with one lever, without switching between drive modes. We're still installing an R&D knob on the dash, so we can put the motor in neutral and drive mode. We won't be using reverse via the knob, but we can use it to engage regen, to use the rotation of the prop shaft to charge the batteries. Speaking of that lever, of course we're keeping the throttle lever of the main diesel engine. And the pole is already there, so we can just add an extra digital throttle handle to control the Tesla motor. With the digital signal from this control handle, we can, with some detours, control the torque request, the regeneration request and the signal for forward and reverse. But before we can test it, the Tesla motor still needs to be cooled. And just as I was about to connect the Tesla to our central coolant system, Dad remembered that aluminum, which is what big chunks of the Tesla coolers are made of, is sensitive to which coolant is used. So it turns out the Tesla is not compatible with the coolant that we use in our central cooling system. Which is a small setback, but it can be solved quite easily with a heat exchanger, an extra pump and a small expansion tank. We are filling this one with green coolant. So now we have very standard blue coolant in our central coolant system, red coolant in the floor heating system, and green for the Tesla system, to make it easy to keep them apart. Not that the color says anything about what type of coolant it is, because that's different for each brand. Now we can find out if the coolant pumps are connected to the right signal outputs from the VCU, so that they started on internal temperature. And we can check if there's no more air in the system. With that working, I took down the throttle handle from the poop deck to test the motor for the first time. So far, so good. Now all we need is to reinstall the drive belts and align the motor to the shaft. And prepare ourselves for the moment of truth. And before we do anything else, I want to see what happens if we put the diesel motor in gear and have the Tesla work as a generator. The next step is taking the throttle handle back up and taking her for a little spin. And boy, this is a weird experience. It's hard to describe, but it's so silent you can't hear the motor it's putting in the work. You can, for the first time, hear the bow thruster, all the way from the aft deck. But with the propulsion, all your senses tell you nothing is happening. Inside the engine room it's not silent. We have 2 coolant pumps and 1 gearbox oil pump, all making some noise. But you can't hear that outside. But the boat is moving and everything's holding up. It also feels like we're moving quite fast. But For this test run, we didn't have any displays hooked up yet, so I don't know how fast. And we should also be able to see live battery data on the navigational displays. We'll have to test that later, on some real shakedown trips to real places to get some real live data. I know I haven't made a lot of videos in the past months. This electrification process has taken up a ton of time, also in the evening hours. But now that this whole side project is kind of in the completion phase, we have more time to focus on winches, sails and interior. Preparations to take her on some real life test cruises. Which should also take up less time, so I can focus again on making some more regular videos. But this is all for now. If you have any questions or remarks, please let us know in the comments. Thank you for watching and I'll see you next time.